40 billion Earth-sized planets are orbiting stars in the habitable zones of our galaxy right now. 40 billion worlds where water could flow in liquid form, where chemistry could cross that invisible border, separating inert matter from living matter. 40 billion natural laboratories where the experiment of life may have already begun, may have already succeeded, may have produced civilizations, languages, cities, telescopes aimed at the sky with the same question as ours. And yet, in 65 years of systematic searching, with the most sensitive instruments ever built by the human species, the result is a single number. Obsessive, relentless, unforgiving, 0, not one signal, not one whisper, not the slightest trace of an intelligence other than our own in a cosmos that has had 13.8 billion years to produce one. That 0 is not a void. That 0 is data. And that data tells a story nobody wants to hear. To understand just how abnormal this silence is, we need to go back to a summer lunch in a cafeteria in New Mexico in 1950. The Los Alamos National Laboratory, where the atomic bomb had been designed 5 years earlier, still housed some of the most brilliant minds on the planet. That day, 4 physicists were walking toward the cafeteria: Enrico Fermi, Edward Teller, Herbert York, and Emil Konopinski. The conversation was light. Someone had mentioned a New Yorker cartoon about flying saucers. UFO reports were making headlines that week, and the 4 men were joking as they sat down. Then, in the middle of a bite, Fermi asked a question that silenced the table. "Where is everybody?" The other 3 immediately understood what he meant. Fermi wasn't talking about flying saucers. He was talking about math. The Milky Way contains between 200 and 400 billion stars. It's roughly 13.6 billion years old. A technological civilization traveling at just 1% of the speed of light, a pace well within anything that would require exotic physics, could cross the entire galaxy in 10 to 100 million years. That sounds like a lot until you compare it to the age of the galaxy itself. 100 million years is less than 1% of the Milky Way's lifespan. There has been enough time for this to happen thousands of times over. Fermi did calculations on a napkin right there at the table. The numbers weren't close. They weren't ambiguous. Even with conservative assumptions about the number of stars with planets, the frequency of life arising, and the survival span of civilizations, the galaxy should be teeming with evidence of intelligent activity. Spacecraft, signals, engineering on a scale visible across interstellar distances. There should be something. There was nothing. The question landed differently from an ordinary scientific puzzle. Most problems in physics have a clear path toward investigation. You build an instrument, you run an experiment, you collect data. But Fermi's question pointed at an absence, and absences are harder to study. You can't aim a telescope at silence and learn why it exists. If you compress the entire history of the Milky Way into a single calendar year, with the Big Bang on January 1st and today on December 31st, 100 million years would represent about 2.5 days. A colonization wave moving at 1% of light speed would cross the galaxy in a long weekend. The galaxy has had the equivalent of 365 days. The universe had time. It had space. It had the raw materials. Every generation of stars produced heavier elements as it died, seeding the next generation with more complex chemistry. If this exploration captivates you, a simple thumbs up and a subscription would help us enormously, and it means a lot to us. Fermi expected someone to find the flaw in the reasoning. Nobody did. And for 10 years after that lunch, the question hung in the air because nobody had the tools to search. Then one man decided to stop asking and start listening. On April 8, 1960, a 29-year-old astronomer named Frank Drake aimed the 85-foot radio telescope at Green Bank, West Virginia, at 2 nearby stars, Tau Ceti and Epsilon Eridani. He tuned to 1,420 megahertz, the emission frequency of neutral hydrogen, the most abundant element in the universe. Giuseppe Cocconi and Philip Morrison had proposed this frequency in a paper published in Nature in 1959, arguing it was the logical channel for interstellar communication. Any technological civilization would know the hydrogen line. It was the obvious place to listen. Drake called his project Ozma after the Queen of the Land of Oz. For roughly 150 hours, he listened. At one point, a strong pulse signal came in and the team froze. It turned out to be a high-altitude military aircraft. After that false alarm, the rest was silence. But Project Ozma carried within it an assumption that would take decades to correct. Drake, and nearly every researcher in the field, thought planets were rare. When Drake convened a conference at Green Bank in November 1961, 10 participants, including Carl Sagan, they worked out what became the Drake equation. It wasn't really an equation in the mathematical sense. It was a framework, a way of organizing ignorance. You multiply the rate of star formation by the fraction of stars with planets, by the fraction of those planets that could harbor life, by the fraction where life actually develops, by the fraction where intelligence emerges, by the fraction that builds detectable technology, by the average lifespan of those civilizations. The second variable, the fraction of stars with planets, was designated FP. Drake and his colleagues set it at 0.2, or 1 in 5 stars. It was a guess, and it seemed generous at the time. Many astronomers thought planetary formation required unusual conditions. They were wrong by a factor of 5. Between 2009 and 2018, NASA's Kepler Space Telescope observed roughly 150,000 stars, watching for the tiny dips in brightness caused by planets transiting in front of them. Kepler confirmed 2,783 exoplanets. The statistical analysis that followed upended the field. Virtually every star in the Milky Way has at least one planet. The fraction FP went to effectively 1.0. Every star. To understand what this did to the calculation, take the estimated 200 to 400 billion stars of the Milky Way and multiply by 1 instead of 0.2. The number of planets jumped by a factor of 5 overnight. Further analyses of Kepler data estimated roughly 40 billion Earth-sized planets orbiting in the habitable zones of their stars, in our galaxy alone. 40 billion worlds where liquid water could exist on the surface. That's roughly 5 planets for every human being alive today. This was supposed to be good news. More planets means more chances for life, more chances for civilizations, more chances for contact. Instead, this discovery made the silence catastrophically worse. If the real estate had always been this abundant, the question was no longer, are there enough planets? The question became, with 40 billion potential homes, why is nobody there? Every new exoplanet discovered tightened the paradox. The galaxy wasn't short on places for life to begin. Something else was stopping it. Years after Ozma, a graduate student accidentally found something that everyone initially thought was the answer. In 1967, Jocelyn Bell Burnell was analyzing data from a radio telescope at Cambridge designed to study quasars. She noticed a signal, a rapid, precise pulse repeating every 1.33 seconds. Nothing known in nature pulsed with that regularity. The research team labeled the source LGM1, Little Green Men. They were half joking, but only half. For weeks, the possibility of an artificial origin remained on the table. Then a second pulsing source was found in a different part of the sky, and then a third. The explanation turned out to be rotating neutron stars, collapsed stellar cores spinning at extraordinary speeds, and sweeping beams of radio energy like a lighthouse. The signals were natural. They were called pulsars. The episode mattered for 2 reasons. It demonstrated that the universe produces phenomena that mimic intelligence with uncomfortable precision. A perfectly timed pulse repeating without variation looks engineered. It wasn't. Nature can be deceptively regular. 10 years after LGM1, the exact opposite happened. On August 15, 1977, Jerry Eman, a volunteer astronomer working with the Big Ear Radio Telescope at Ohio State University, was reviewing printouts of the previous day's data. Big Ear was a flat reflector telescope that scanned strips of sky as the Earth rotated. The data came out on continuous paper, columns of alphanumeric characters representing signal intensity at different frequencies. One sequence jumped off the page. At exactly 1,420.456 megahertz, the hydrogen line, a signal appeared that was roughly 30 times stronger than the background noise of space. The peak intensity exceeded 250 Janskys. It lasted 72 seconds, which matched exactly how long a celestial source would remain in Big Ear's beam as the Earth rotated. The signal behaved exactly the way an extraterrestrial transmission should behave. Eamon circled the character sequence, 6EQUJ5, and wrote a single word in red ink in the margin. Wow. To put 250 Janskis in physical terms, imagine the difference between a whisper and a scream in a quiet room. The cosmic background at that frequency is the whisper, the wow. Signal was someone screaming directly into the microphone, at exactly the frequency Cocconi and Morrison had identified in 1959 as the Universal Communication Channel. The signal never repeated. Eamon and others pointed Big Ear at the same patch of sky hundreds of times over the following years. Nothing. Other telescopes searched the same coordinates. Nothing. The signal came from the direction of the constellation Sagittarius, from a region with no notable star or object. For 40 years, the wow. Signal remained the strongest candidate for an extraterrestrial transmission in the history of the search. A 72-second burst, then silence. What happened to that signal, and to the telescope that detected it, forms one of the strangest chapters in all of science. The Big Ear Radio Telescope operated from 1963 until its demolition between 1997 and 1998. The land in Delaware, Ohio, was sold to a developer. The developer built a golf course. The instrument that had captured humanity's most promising signal for extraterrestrial contact was bulldozed so people could play 18 holes on the ground where it once stood. If you visit that site today, there's nothing to indicate what once listened to the sky from that spot. The wow. Signal remained unexplained for decades. Dozens of hypotheses circulated: satellite interference, classified military transmission, equipment failure. None fit. The frequency was too precise, the behavior too consistent with a deep sky source, the intensity too high for any known terrestrial or orbital origin. Then, in 2017, Antonio Paris, an astronomer at St. Petersburg College, proposed an answer that seemed to close the case. Two comets, designated 266P/Christensen and P/2008Y2, were in the general area of Big Ear's beam on the night of August 15, 1977. Paris argued that the hydrogen clouds surrounding these comets could produce emission at 1,420 megahertz, mimicking exactly the signal Eamon had detected. Comets carry hydrogen. The frequency matched. Several media outlets reported the mystery as solved. The explanation was comfortable. It gave the wow signal a natural origin. It allowed the scientific community to move on, and for a few years, many did. Except there were problems from the start. Other astronomers pointed out that the comets in question weren't actually in the correct beam position on that date. Big Ear had two feed horns, and the geometry didn't place either comet in the right one. More fundamentally, comets emit radio signals at 1420 megahertz at extremely low power. The kind of emission a hydrogen cloud around a small comet can produce is orders of magnitude weaker than 250 Janskis. It's like proposing that a candle caused a forest fire visible from orbit. The scale was wrong. In 2025, a team decided to go back to square one, directly to the original documents. The physical printouts from Big Ear's August 1977 observing session, pages of dot matrix output that had been sitting in archives for nearly half a century. Nobody had conducted a full, systematic reanalysis of the original data in decades. The results destroyed the comet hypothesis and replaced it with something nobody expected. The researchers used optical character recognition to digitize all 75,000 pages. The flux density of the wow signal well exceeded 250 Janskis. At that power level, the comet explanation collapses entirely. Comets at 1420 megahertz produce emission measured in millijanskis, thousands of times below the observed intensity. So, if it wasn't a comet, and it wasn't terrestrial interference, and it wasn't a satellite, what was it? The new best hypothesis is stranger than all of those explanations, and stranger than aliens. The researchers now propose that the wow signal was a rare superradiance event, sometimes described as a hydrogen maser flare, possibly triggered by a magnetar. In simple terms, under specific unusual conditions, a cold hydrogen cloud can be stimulated to emit a sudden, intense burst of radiation at exactly 1,420 megahertz. If a magnetar, a neutron star with an extraordinarily powerful magnetic field, passes near such a cloud or through it, it can trigger this kind of coherent emission. The result is a one-time cosmic shout of perfectly tuned radiation, powerful, brief, never repeating. Imagine a balloon filled with gas that has been slowly pressurized for thousands of years. One day, a spark hits it. The balloon doesn't pop slowly, it releases all its energy in a single flash. Then it's gone. The conditions that built it no longer exist. You could watch that point in the sky for another 50 years and never see it again. The wow signal wasn't intelligence. It wasn't comets. It was something the universe produced naturally, but so rarely that nobody had predicted it. The cosmos generated a signal that perfectly mimicked what we expected from an alien civilization, at exactly the frequency we were listening on. And it did it through pure physics. This mattered beyond the wow signal itself. It established a pattern that would repeat throughout the history of the search. Every time scientists thought they'd found evidence of technology, the universe offered a natural explanation nobody had anticipated. Pulsars mimicked regular transmissions. Comets were accused and then acquitted. Superradiance produced a perfect false positive. And the question got harder. If the universe keeps generating false positives that look exactly like intelligence, how would we recognize the real thing if it ever showed up? Let's go back to the Drake equation and look at what happened to every variable scientists could actually measure. In 1961, the fraction of stars with planets was estimated at 0.2. Kepler proved it was closer to 1.0. The star formation rate in the Milky Way was estimated at 1 per year. Modern observations place it between 1 and 3. The number of potentially habitable planets was thought to be small. It turned out to be 40 billion in our galaxy alone. And then there's biogenesis, the origin of life from non-living chemistry. Earth formed approximately 4.54 billion years ago. The last universal common ancestor of all life on Earth, known by the acronym LUCA, existed approximately 4.2 billion years ago. The gap is only 300 to 400 million years, and much of that early period had a molten surface, bombarded by asteroids, essentially uninhabitable. Life didn't wait for ideal conditions. It appeared almost as soon as conditions allowed, maybe even before. If biogenesis is easy, and every piece of evidence from Earth suggests it is, then life should be common across the galaxy. Every measurable variable in the Drake equation has moved in the optimistic direction since 1961. More stars have planets. More planets sit in habitable zones. Life starts faster than anyone predicted. The galaxy should be teeming with life. The result of 65 years of searching is 0. This means the filter must lie at one of the variables we can't yet measure. Something is eliminating civilizations from the galaxy. The question is what and when in the chain it happens. In 1996, an economist looked at exactly this problem and gave the bottleneck a name. Robin Hanson wasn't an astronomer. He wasn't a physicist. He was an economist at George Mason University. And in 1996, he published a paper that reframed the Fermi paradox in terms a betting market would understand. His reasoning went like this. Between a dead rock and a civilization spreading across the galaxy, there is a long chain of steps. Form a planet, develop life, evolve complex cells, produce intelligence, build technology. Survive long enough to expand. If the galaxy should be full of civilizations but isn't, at least one of these steps must be extraordinarily improbable. A bottleneck so severe that almost no one gets through it. Hansen called it the Great Filter. The concept is pure probability. You don't need to know which step is the hard one. You just need to accept that the silence proves a filter exists somewhere in the chain. The math demands it. If every step were reasonably probable, the galaxy would be visibly colonized. It isn't. Therefore, at least one step has a pass rate near 0. The crucial question isn't whether the filter exists. The silence answers that. The crucial question is where it sits, and that's where the concept becomes personal. If the Great Filter is behind us, somewhere in the early steps, then we've already passed through it. Maybe the origin of life is the hard part and we got lucky. Maybe the jump from single-celled organisms to complex multicellular life is nearly impossible, and Earth just happened to clear that hurdle. If the filter is behind us, we're rare but safe. The hard part is over. If the Great Filter is ahead of us, somewhere in the later steps, then every civilization that reaches our level of technology eventually hits a wall it can't survive. Nuclear war, environmental collapse, engineered pandemics, something we haven't even imagined yet. In this scenario, the silence is a graveyard. Every civilization that got as far as we have is dead or dying. To make the stakes concrete, imagine 100 civilizations starting the journey from simple chemistry to interstellar travel. If the filter is behind us, 99 of them never get past microbial life, and we're the one that did. Dangerous but accomplished. If the filter is ahead, all 100 develop technology and are destroyed before they can leave their home planet. We've built the rockets, we've built the radio telescopes. We just haven't yet crossed the line that kills the others. For 2 decades after Hansen's paper, the debate remained roughly balanced, good arguments on both sides. No decisive evidence either way. Then, in 2024, 2 papers landed that tipped the weight heavily toward the worst scenario. Both proposed filters ahead of us, and both describe mechanisms that are already underway. Michael Garrett is an astrophysicist. In 2024, he published a paper proposing that artificial intelligence is the great filter. His argument rested on a timeline. Earth's first radio transmission occurred in 1897 when Guglielmo Marconi sent signals over a distance of about a mile. 127 years later, in 2022, generative AI systems began operating at a level that surprised even their creators. The leap from the first radio wave to sophisticated AI took just over a century. Garrett's model assumes any technological civilization follows a similar trajectory because the underlying pressures are the same. Once you develop electronics, the path toward increasingly autonomous computing systems isn't optional. It's driven by economic competition, military advantage, and the fundamental logic of improving tools. Garrett's estimate for the window between developing AI and being destroyed or fundamentally altered by it: roughly 200 years, not thousands, not millions, centuries. That's the total duration a civilization might emit detectable signals while still existing in a form that would produce those signals. Apply that window to the Milky Way. The galaxy is 13.6 billion years old. A civilization's detectable phase lasts 200 years. That's like trying to photograph a specific lightning bolt during a thunderstorm that lasts 4 million years. Even if millions of civilizations have existed throughout galactic history, the probability of any two overlapping within their 200-year windows is infinitesimal. The model doesn't require AI to physically destroy a civilization. It also accounts for scenarios where AI transforms a civilization into something unrecognizable, a species that merges with its machines, or is replaced by them, or stops broadcasting because the AI has no interest in radio communication. The observable signature vanishes. The civilization goes dark. Look at Earth's own trajectory. Military radars, the most powerful signal we produce, operate at roughly 10 to the 14th power watts in directional bursts. Those signals are detectable by a Green Bank-class telescope out to about 200 light-years. That sounds like a lot. It isn't. 200 light-years covers roughly 15,000 stars. The Milky Way contains between 200 and 400 billion. Our loudest screams reach 0.004% of the galaxy, and we're getting quieter every year. Fiber optic cables carry data through glass, not through the air. Cellular networks use low-power transmitters aimed at the ground, not the sky. Digital signals are compressed and encrypted, making them indistinguishable from random noise to a distant receiver. Military radars are shifting to phased arrays that focus energy in narrow beams, rather than spraying it everywhere. Earth in 1970 was a campfire visible for miles. Earth in 2026 is a flashlight pointed at the ground. To put 200 years in physical terms, imagine the entire history of the Milky Way as a road 1 kilometer long. 200 years represents roughly 1/5 of a millimeter. That's the segment of pavement during which a given civilization is audible. The rest of the kilometer is silence, before and after. Garrett's paper wasn't the only one proposing a filter ahead of us. In February 2026, a researcher proposed something that doesn't require machines at all. Darren Dugan proposed a different mechanism for civilizational extinction. His filter doesn't require machines turning on their creators. It doesn't require war or asteroid impacts or any external catastrophe. It requires only one thing: a species smart enough to decouple reproduction from survival, and it's already measurable in the demographics of every industrialized nation on Earth. Birth rates are falling across the developed world as a direct consequence of prosperity and choice. Dugin's model treats this as universal, an inevitable property of any intelligent species capable of controlling its own fertility. South Korea's total fertility rate in 2024 was 0.72. That means for every 2 adults, fewer than 1 child is born. Replacement level is 2.1. South Korea isn't at half of replacement, it's at a third. Japan is at 1.2, Italy at 1.24. China dropped below replacement in 2022 and is accelerating downward. The United States fell below replacement in 2021. These aren't projections, they're census figures. Dugin's model doesn't treat fertility decline as a crisis to be solved. It treats it as a thermodynamic inevitability, the same way entropy is inevitable. His argument works like this. In any species that evolves intelligence, individuals eventually gain the ability to choose whether they reproduce. Once that choice exists, the calculus changes. Children become expensive in time and resources. In a subsistence society, children are labor. In a technological society, children are a cost. Every government that has tried to reverse the trend has failed. Pro-natalist policies in Scandinavia, Japan, Singapore, Hungary, all have produced temporary bumps of a few percentage points before the decline resumed. Dugin's projection traces current global trends into the future. Human population peaks around 2080 at approximately 10 billion, then begins a decline that accelerates with each generation. By 2500, his model estimates fewer than 100 million humans on Earth. By 3000, functional extinction. A species that once covered an entire planet, dissolved into empty maternity wards. And if this is universal, if every intelligent species that takes control of its own reproduction follows the same curve, it explains the silence without invoking any catastrophe at all. No nuclear war, no asteroids. Just a slow, quiet erasure across every inhabited world in every galaxy. Civilizations arise, develop technology, decouple sex from reproduction, decouple reproduction from survival, and dissolve within a few hundred generations. The galaxy fills with ruins, not conquerors. Garrett's AI window of 200 years and Dugin's depopulation curve of 500 to 1,000 years, these filters aren't mutually exclusive. A civilization could face both simultaneously, and both papers were published within 2 years of each other, based on trends already visible in human data. But both of these filters assume civilizations destroy themselves or fade away. There's another possibility, one that gets talked about less because it doesn't involve death at all. What if civilizations don't die? What if they just go quiet? Here's a fact that undermines the entire premise of the search for extraterrestrial intelligence. Earth is getting quieter. In the 1960s and 70s, humanity was loud. Omnidirectional radio broadcasts, television signals, and military radar systems pumped electromagnetic radiation into space in every direction. Military radars, the most powerful signals Earth produces, reach roughly 10 to the 14th power watts in directional bursts. A telescope the size of Green Bank, 330 feet in diameter, could detect those signals out to about 200 light-years. That sounds like a lot. It isn't. 200 light-years covers roughly 15,000 stars. The Milky Way contains between 200 and 400 billion. Our loudest screams reach 0.004% of the galaxy, and we're getting quieter every year. Fiber optic cables carry data through glass, not through the air. Cellular networks use low-power transmitters aimed at the ground, not the sky. Digital signals are compressed and encrypted, indistinguishable from random noise to a distant receiver. Military radars are shifting to phased arrays that concentrate energy in narrow beams rather than spraying it everywhere. Earth in 1970 was a campfire visible for miles. Earth in 2026 is a flashlight aimed at the ground. A civilization 1,000 years ahead of us might communicate entirely through narrow-beam lasers, quantum encrypted channels, or technologies we haven't invented yet. Their communication would be invisible to us because efficiency naturally selects for directed low-waste transmission. It's like the shift from town crier to postal mail. The information flow increased by orders of magnitude, but the noise dropped to nothing. Maybe the silence is evidence of graduation, not extinction. But some scientists weren't content to just listen for leaks. They wanted to search for something bigger, something physical you could see across the entire galaxy. In 2024, a project called Hephaestus published results that made international headlines. The team had scanned roughly 5 million stars within a radius of 1,000 light-years, looking for something nobody had systematically searched for at that scale before: Dyson spheres. The concept dates back to physicist Freeman Dyson in 1960. A civilization sufficiently advanced, he argued, would eventually need more energy than a single planet can provide. The logical next step would be to build a structure around its star, a shell or swarm of collectors capturing the star's entire energy output. Such a structure wouldn't be invisible. The laws of thermodynamics guarantee it. It would absorb the star's visible light and re-emit that energy as infrared radiation, waste heat. That's exactly what Hephaestus found. 7 candidate stars showed anomalous mid-infrared excess that couldn't be easily explained by known astrophysical processes. The response was immediate. Media published headlines about possible alien megastructures. The follow-up analysis arrived in 2025. Independent teams re-examined the 7 candidates using additional infrared and optical data. What they found weren't alien megastructures, it was background contamination. The anomalous infrared excess was real. It just wasn't coming from the stars, it was coming from objects behind them, billions of light-years farther away. Dust-obscured galaxies and active galactic nuclei. The supermassive black holes at the centers of distant galaxies spewing enormous amounts of energy as they consume surrounding matter. The universe had done it again. It had perfectly mimicked the signature of advanced technology using nothing but random cosmic geometry and warm dust. The pattern is consistent and uncomfortable. Every time we think we found something, nature offers a natural explanation nobody predicted beforehand. The universe is actively deceptive. It produces phenomena that look engineered, that pass our filters, that survive initial scrutiny, then collapse into mundane physics when examined more closely. 5 million stars, and not a single megastructure, not a single hint of engineering at any scale. But false positives and cosmic mirages are only one category of explanation for the silence. There's a darker one. What if civilizations are out there, real, and they stay hidden on purpose? In 2008, Chinese science fiction writer Liu Cixin published the second novel in his 3-body problem trilogy. It was called The Dark Forest. The book proposed an answer to the Fermi paradox that was elegant and deeply disturbing. The universe is full of civilizations. They're all silent, because revealing your position is equivalent to committing suicide. The logic builds from 2 axioms. First, survival is the primary need of every civilization. Second, civilizations grow and expand continuously. But the total matter and energy of the universe do not grow. These 2 axioms produce a problem. Resources are finite. Civilizations are potentially infinite. Any civilization that encounters another faces a choice: cooperate or destroy. But cooperation requires trust, and trust requires communication. And communication reveals your position. You can't verify another civilization's intentions. They might be peaceful today and hostile in 1,000 years. They might be technologically inferior today and superior in a century. The only way to guarantee your safety is to strike first, before the other civilization becomes a threat. And because every civilization knows this, every civilization that has survived long enough to exist right now has learned the same lesson. Stay quiet, stay hidden. Shoot anything that makes noise. Imagine a forest at night. It's full of hunters. Every hunter knows the forest is full of other hunters. Nobody can see more than a few feet. Every sound, every movement could draw a bullet. The rational strategy is to stand perfectly still and shoot at any noise. The The cosmos, in this model, is filled with armed civilizations standing motionless in the dark. The hypothesis has a specific physical implication. A dark forest civilization wouldn't build Dyson spheres because they're visible across the galaxy. It wouldn't emit radio signals because radio signals reveal position. It wouldn't expand aggressively because expansion creates a detectable footprint. It would minimize its observable signature in every possible way. It would look, from the outside, exactly like the silence we observe. And this leads directly to a real controversy playing out right now on Earth, one that has divided the scientific community and involves the question of whether we should be shouting into that forest. In 1999, a Russian astronomer named Alexander Zaitsev did something that no international body had approved and no scientific consensus had endorsed. He used the Yevpatoria planetary radar in Crimea, a dish originally built for deep space communication with Soviet probes, to transmit a powerful, targeted message towards several nearby star systems. He called it Cosmic Call. Zaitsev consulted nobody in the scientific community before transmitting. He sought no government approval. He requested no international review. He didn't need to, because there is no binding international protocol governing deliberate transmissions into space. None. There are guidelines. The International Academy of Astronautics has a set of recommendations, but they're voluntary. No treaty, no law, no enforceable agreement prevents anyone with access to a powerful enough transmitter from broadcasting a message into the cosmos right now, today, announcing humanity's existence and location to whoever is listening. David Brin, the physicist and author, called this reckless and potentially catastrophic. If the dark forest hypothesis had even a low probability of being correct, he argued, deliberately transmitting was equivalent to lighting a campfire in a forest full of predators. Seth Shostak at the SETI Institute took the opposite view. His argument was practical. Earth's military radar systems have been leaking detectable signals into space for decades. Anyone within 100 light years who has the technology to threaten us already knows we're here. Deliberately transmitting changes nothing. Hiding is pointless because we were never hidden. Think of it this way. You're standing in a dark room and you've been coughing loudly for 70 years. Someone suggests maybe you should stop coughing, but you've been coughing the whole time. If something in the dark wanted to find you, it already has. The debate has never been resolved. It can't be, because the underlying question is unanswerable. Is the universe dangerous or not? And meanwhile, the tools we've built to find out keep getting destroyed. On December 1st, 2020, the 900-ton receiver platform of the Arecibo Observatory broke free from its cables and crashed through the 1,000-foot radio telescope dish below. The collapse wasn't sudden. Engineers had warned about cable degradation for months. The National Science Foundation chose not to rebuild. Arecibo had been used for SETI searches, the Project Phoenix program, radar mapping of near-Earth asteroids, pulsar research, and atmospheric studies. It was one of the most productive scientific instruments ever built, and it's gone. But Arecibo wasn't the first. Big Ear in Ohio, demolished for a golf course. The Allen Telescope Array put into hibernation in 2011 for lack of $1.5 million per year. For context, a single F-35 fighter jet costs $80 million. NASA's SETI program, defunded by Congress in 1993 after a single year of operation. $12 million, roughly the cost of 600 feet of interstate highway. If you were designing a civilization that would never detect an extraterrestrial signal, this is roughly how you'd go about it. In 2015, Yuri Milner, a Russian-Israeli billionaire, stood on a stage in London alongside Stephen Hawking and announced breakthrough. Listen, $100 million over 10 years, dedicated to the most thorough search for extraterrestrial intelligence ever attempted. The program secured access to some of the most powerful radio telescopes on the planet: Green Bank in West Virginia, Parkes in Australia, Meerkat in South Africa. By 2024, the project had scanned roughly 1 million nearby stars. It had accumulated more than 2 petabytes of data. Its sensitivity was extraordinary. Breakthrough Listen could detect a transmitter producing 10 to 13 watts from neighboring star systems. If anyone nearby was making a deliberate effort to be heard, its instruments would have picked it up. Nothing did. 2 petabytes of silence. Then in 2020, one of Breakthrough Listen's own instruments picked up something that made the entire team hold its breath. Parkes detected a narrowband signal at 982.002 megahertz. Narrowband signals are significant because natural astrophysical sources almost always produce broadband emissions. A signal concentrated on a single frequency is one of the hallmarks of an engineered transmission. And this one appeared to come from the direction of Proxima Centauri, the nearest star to our own, at 4.24 light-years. The signal was designated BLC-1, Breakthrough Listen Candidate 1. The first signal the project had ever judged promising enough to merit a formal candidate designation. BLC-1 drifted in frequency. When a signal comes from a source on a rotating planet, the rotation causes a Doppler shift, a gradual change in the observed frequency. The signal appeared only when the telescope was pointed at Proxima Centauri. When the dish moved to a reference direction, the signal vanished. When it swung back to Proxima, the signal returned. BLC-1 passed the standard test. It wasn't the answer. In 2021, the team published an analysis showing BLC-1 was almost certainly human-generated radio interference. The most likely source was electronics operating near the Parkes telescope itself. The most exciting candidate in decades had been generated by human technology a few hundred feet from the antenna. Imagine hearing a knock at your door in the middle of the night. You check, no one. You open, no one. You step outside and hear the knock again. Then you realize it's coming from the pipes inside your own wall. In March 2023, an instrument called COSMIC came online at the Very Large Array in New Mexico. The VLA is an icon of radio astronomy, 27 antennas, each 82 feet in diameter, arranged in a Y shape in the desert. COSMIC piggybacks on normal astronomical observations. Whatever the VLA is observing on a given night, COSMIC processes the same data in parallel, searching for narrowband signals that might indicate a technological source. In its first 11 months of operation, COSMIC observed more than 950,000 unique fields, covering 267,510 individual stars. The result: 0 techno-signatures. In 2024, the Murchison Wide Field Array in Western Australia surveyed 2,800 entire galaxies for techno-signatures. Nothing. In October 2024, the Allen Telescope Array conducted the longest continuous SETI observation ever directed at a single target. 28 hours pointed at TRAPPIST-1. 2,264 candidate signals, all of terrestrial origin. In July 2025, the third confirmed interstellar object entered the solar system, 3I/Atlas. Breakthrough. Listen tracked it. 7 hectares of observation. 74 million narrowband signals recorded. After filtering, 211 candidates. Final result: 0. The searches are orders of magnitude beyond anything Frank Drake could have imagined when he aimed his 85-foot dish at 2 stars in 1960. The instruments are more sensitive. The frequency coverage is broader. The analysis is faster, with artificial intelligence accelerating Breakthrough Listen's data processing by a factor of 600. And the number hasn't changed. It was 0 in 1960. It's 0 after 1 million stars from Breakthrough Listen. 0 after 950,000 fields from COSMIC. 0 after 74 million signals from an interstellar visitor. For decades, there was a standard defense against the silence. Jill Tarter, who spent 35 years leading the search, put it this way: imagine you want to know if there are fish in the ocean. You walk to the shore, scoop up a bucket of water, look inside, and find nothing. Would you conclude the ocean has no fish? That was the argument. All of SETI, every dish aimed at every star, amounted to a bucket scooped from a cosmic ocean. It sounded reasonable, it sounded humble, and for a long time, it was enough. But the argument has stopped working. The problem is the accumulation of data. SETI at home ran for 21 years. Millions of volunteer computers processed 12 billion candidate signals. Breakthrough. Listen has scanned 1 million stars. COSMIC has covered 950,000 fields in less than a year. The MWA surveyed 2,800 galaxies. The combined result is still the same number, Statistical models built on 6 decades of null results now estimate fewer than 1 to 5 detectable technosignatures per century in the entire Milky Way. That's no longer a bucket of water. That's a measurement. There's a molecule biologists have relied on for decades as an indicator of life: free oxygen. Free molecular oxygen is chemically reactive. Leave a planet alone for a few million years without something continuously replenishing the oxygen supply, and it vanishes entirely from the atmosphere. On Earth, that something is photosynthesis. Oxygen became the gold standard biosignature. The logic seemed clean. If you detect free oxygen in the atmosphere of a distant planet, something biological is probably maintaining it. Then, in 2024, a research team discovered oxygen being produced at the bottom of the Pacific Ocean, not by anything alive. The source was polymetallic nodules, chunks of metallic ore sitting on the ocean floor at depths where no surface light reaches. These nodules contain manganese, nickel, cobalt, copper, and other metals that generate small but measurable electrical voltages through natural electrochemical reactions. The voltage is sufficient to split seawater molecules into hydrogen and oxygen through electrolysis. No biology required. Imagine discovering that the smoke detector you've relied on your entire career also goes off randomly when nobody's cooking and nothing's burning. If oxygen can be produced without life on Earth, in Earth's own oceans, it can be produced on a rocky planet orbiting a red dwarf 40 light-years away. One of astrobiology's most foundational assumptions just cracked. The planet K, 2-18b, orbits a red dwarf star 124 light-years from Earth. In 2023, the James Webb Space Telescope analyzed the starlight passing through its atmosphere and detected what appeared to be dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton. The headlines were immediate and global. Then the data was examined more closely by independent teams. The signal sat in the noise floor of the observation. The statistical confidence of the detection fell below the threshold most scientists consider reliable. By early 2025, the scientific consensus had shifted. The signal was most likely an artifact of the data reduction process, a ghost in the numbers rather than a molecule in the sky. The investigation doesn't conclude with a resolution. It concludes with a measurement. The universe has had 13.8 billion years and hundreds of billions of stars. On at least one planet, life started almost immediately and eventually produced a species that built radio telescopes and asked, "Where is everybody?" The silence is information. Something in the journey from microbe to interstellar civilization is either incredibly difficult, incredibly brief, or both. In 13.8 billion years, it has either never been accomplished or never lasted long enough to leave a trace. This isn't philosophy. This is what the data says, and it leads to one last uncomfortable place. Earth has been transmitting for about 100 years. The first radio signals powerful enough to escape the atmosphere date from the early 1920s. Military radars from the mid-20th century are the loudest thing this planet has ever produced. Those signals expand outward at the speed of light in a sphere that currently covers roughly 15,000 stars. A civilization with a Green Bank-class telescope aimed at our star during the right century could detect us. But Earth is already getting quieter. The shift from broadcast TV to streaming, from analog radio to digital compression, from omnidirectional radar to phased arrays, all of it shrinking the footprint year by year. If Garrett's model is right, the window between the first radio signal and AI consuming a civilization is 200 years. Earth is at year 127. If Dugan is right about demographic decline, the window stretches to 500 or 1,000 years. Take the generous number, 1,000 years of detectability in a galaxy that's 13.6 billion years old. That's a ratio of 1 to 13.6 million. For another civilization to notice us, it would need to exist at the same time, equipped with instruments pointed in our direction, tuned to the right frequency during our window. We'd need the same from theirs. 2 fireflies blinking in a forest the size of a continent. Each flash lasts a fraction of a second. Each firefly is real. They miss each other by 100,000 years and never know the other existed. The most common outcome might be the simplest. Civilizations arise, flicker for a geological instant, and go quiet. The galaxy might be full of ruins, or full of species silenced by physics rather than by choice. It might contain thousands of civilizations that existed millions of years apart, never coinciding. Any of these possibilities produces the same observable result: 0. FAST continues to listen in Guizhou. The James Webb Space Telescope continues analyzing exoplanet atmospheres. Breakthrough. Listen processes data 600 times faster than it did 5 years ago. The question Enrico Fermi asked at lunch in 1950 has not been answered. The instruments are more powerful than they have ever been, and the window, whatever its true duration, is still open. For now, we are listening. The silence listens back, and in that silence lies perhaps the most profound answer science can offer to a species searching for its place in the cosmos. Not that we are alone, but that the window for not being alone is so narrow, so fragile, so fleeting on a cosmic scale that finding it would be like catching a snowflake in a hurricane. The snowflake exists. The hurricane is real. The probability of contact remains a number so close to 0 it takes a mathematical magnifying glass to distinguish it from nothing. And yet, the antennas turn. The data accumulates. The algorithms sharpen. Somewhere in the mountains of Guizhou, 1,600 feet of aluminum face the night sky, gathering the universe's whispers with a patience only a machine can have. FAST is currently re-examining the last 100 candidates left by 21 years of distributed computing from SETI at home. 12 billion signals reduced to 100 unresolved anomalies that the software couldn't classify as terrestrial interference, satellite contamination, or instrumental artifact. Each one receives multiple observation sessions at different times to account for the possibility that a signal might be intermittent or directional. If even one of those candidates produces a confirmed, repeatable detection that can't be attributed to terrestrial sources, the framework of this entire investigation changes overnight. To date, FAST has reported nothing from any of the re-observed candidates. The signals that survived 21 years of distributed computing and billions of hours of volunteer processing appear to dissolve under the scrutiny of a better telescope. Meanwhile, the machine learning algorithms developed for Breakthrough Listen now process data 600 times faster than conventional methods. The volume of sky systematically searched per unit of time is growing exponentially compared to just 5 years ago. The silence doesn't prove we're alone. It is consistent with a universe where the window is small, the distances between stars immense, and 13.8 billion years, not enough time for brief flashes of technology to overlap across a galaxy 100,000 light-years wide. The silence is the sound a universe makes when life is common, intelligence is rare, and technology is ephemeral. The sound of countless civilizations blinking in the darkness, each too brief to catch another's eye. The lessons of 40 billion habitable planets and 0 messages received. It is the loudest sound science has ever heard, and it says one thing: whoever you are, wherever you are, enjoy the window. It doesn't stay open long. There is, however, one trail this investigation hasn't yet followed, one that concerns not radio signals or megastructures or deliberate transmissions, but the raw material of life itself, and what the most recent discoveries tell us about how easily it emerges. Because the easier life is to start, the harder the silence becomes to explain. For decades, the dominant theory about the origin of life on Earth was called the RNA world hypothesis. The idea was elegant in its simplicity. Ribonucleic acid, a long-chain molecule capable of both storing genetic information and catalyzing chemical reactions, would have assembled spontaneously from the raw materials of Earth's primordial environment. Once it existed, it could copy itself. The copies introduced errors. Errors that improved the molecule's replication ability were preserved. Natural selection operating at the molecular level took over. The RNA world was attractive because it solved the chicken and egg problem of biology. Proteins need DNA to be coded. DNA needs proteins to be maintained. RNA can do both, poorly but well enough, making it the plausible starting point. Research published between 2022 and 2025 has changed the picture considerably. Multiple independent studies have demonstrated that amino acids, the chemical building blocks of proteins, and RNA nucleotides, the building blocks of RNA, likely co-evolved from the very beginning of prebiotic chemistry on Earth. They didn't appear in sequence, one after the other. They appeared together, interacting in ways that made both components more chemically stable and more functionally capable than either would have been alone. The distinction matters enormously for the Fermi paradox. If the RNA world hypothesis was correct, biogenesis depended on one specific molecule reaching one specific chemical configuration under specific conditions. If the coevolution model is correct, biogenesis looks more like a highway with multiple lanes and on-ramps. There are more chemical pathways leading to a living system. Every revision of the origin of life story over the last 3 years has made biology easier to start, more chemically probable, more likely to occur wherever conditions permit. And every revision has made the silence harder to justify. Because if the path from chemistry to life is a highway, and the universe has had 13.8 billion years to travel it, the total absence of traffic at the destination demands an explanation that chemistry alone cannot provide. Something stops the journey after it starts. Something happens between the emergence of biology and the emergence of a detectable signal. Earth itself offers a disturbing clue about the nature of that something. Life appeared on this planet almost immediately. Earth formed approximately 4.54 billion years ago through gravitational accretion of dust and gas. For the first few 100 million years, the surface was largely molten rock, bombarded by asteroids relentlessly, temperatures exceeding anything compatible with the complex chemistry of biology. Conditions were, by any reasonable standard, appalling for the emergence of living systems. And yet LUCA, the last universal common ancestor, the single organism from which every living thing on Earth descends, existed approximately 4.2 billion years ago. The gap is 300 to 400 million years between the planet forming and confirmed life being present. And much of that window was spent under conditions where life as we understand it couldn't have survived on the surface. To understand how fast this is in geological terms, imagine the entire history of Earth, all 4.54 billion years, compressed into a single calendar year. The planet forms on January 1st. Life appears before the end of February. Dinosaurs don't show up until December. No, humans arrive in the last few minutes of December 31st. February. That's how quickly non-living chemistry turned into biology on this planet. If biogenesis is that easy and that robust, then it should be happening on rocky planets across the galaxy right now, and has been for billions of years. But intelligence took another 4.5 billion years to emerge on Earth. After life appeared, detectable technology, the kind that produces radio signals or infrared waste heat, appeared only in the last century. The bottleneck is clearly not life itself. Single-celled organisms, bacteria, archaea, and their equivalents are probably common across the galaxy. They may be as ordinary as rocks. The bottleneck may not even be intelligence in the strict sense, though estimates of 0.003 to 0.2% of life-bearing planets developing intelligent species make that filter formidable. Earth itself spent over 3 billion years populated exclusively by single-celled life before multicellular organisms appeared. That's not a brief delay, it's most of the planet's history. The real bottleneck may be something even further down the chain, building a technological civilization that persists, building something that doesn't collapse, doesn't fade, doesn't go silent before anyone in the neighborhood has a chance to notice it exists. In 2000, Peter Ward and Donald Brownlee at the University of Washington published Rare Earth, a book that became one of the most influential arguments for why we might be alone. Their case rested on a chain of requirements. Complex life requires a stable climate. A stable climate requires plate tectonics to regulate carbon dioxide, recycle nutrients into the biosphere, and help maintain a planetary magnetic field. Plate tectonics requires a specific internal heat budget and a mantle of the right composition. Earth has all of this. Most planets probably don't. The argument was elegant. We're rare because our geology is rare. Then the models started to diverge. Computer simulations run between 2015 and 2024 gradually undermined the causal chain. Some models showed that plate tectonics on Earth may not have preceded the emergence of complex life. Instead, tectonics might have arisen partly because of complex life. Biological activity at the surface, particularly weathering of rocks by organisms, may have weakened the crust enough to allow subduction to begin. If true, the relationship is reversed. Life doesn't need tectonics. Tectonics needs life. Other simulations produced a different problem. Some models showed that plate tectonics can actually slow atmospheric oxygenation because subduction pulls oxidized material into the mantle. And then there was Pluto. When NASA's New Horizons probe flew past the Pluto system in 2015, it sent back images of geological activity nobody expected. Pluto's surface showed evidence of glacial tectonics. These are worlds billions of miles from the warmth of the nearest star. Nobody had predicted active geology there. Robin Hansen built the Great Filter concept in 1996. 3 decades later, he extended it into something more specific. His Grabby Aliens model begins with a premise that seems obvious but whose consequences are not. If even a small fraction of technological civilizations decide to expand beyond their home star system, traveling at even a modest fraction of light speed, they should visibly reshape the galaxy by now. Obviously and visibly. A single civilization expanding at 1% of light speed would fill the entire galaxy in 10 to 100 million years. Hansen's mathematical model calculates what the galaxy should look like if expanding civilizations exist or have ever existed. They would convert stellar material and planetary resources into megastructures at a scale detectable across thousands of light years. They would harvest energy from stars in quantities producing unmistakable infrared waste heat signatures. They would carve spheres of influence, expanding bubbles of engineered space. The actual galaxy looks nothing like that. Nothing at all. Hansen's calculations show that, for multiple civilizations to coexist in the same galaxy, without encountering each other, they would need average lifespans exceeding 280,000 years. For context, anatomically modern humans have existed for about 300,000 years total, and we have possessed technology capable of interstellar travel for exactly 0 of those years. The evidence from recent research makes the lifespan requirement impossible. Garrett's model gives civilizations roughly 200 years after developing AI. Dugan's model gives them 500 to 1,000 years before demographic collapse. Neither comes close to the quarter-million-year threshold Hansen's geometry requires. The conclusion was brutal. Civilizations don't expand because they don't last long enough to begin expansion. They appear, flicker briefly, and vanish. The galaxy remains exactly as empty as it looks. There exists one hypothesis, the one most working scientists refuse to take seriously, but none can formally refute. That suggests the problem goes deeper than imperfect tools. It suggests we may not be seeing the real universe at all. In 2001, science fiction writer Stephen Baxter published a thought experiment that most astronomers dismissed outright, and none could actually disprove. He called it the planetarium hypothesis. The idea is simple in its construction and disturbing in its implications. If a civilization existed that was sufficiently advanced, thousands or millions of years beyond our current technological level, it could enclose our solar system in a projected simulation, a perfect replica of an empty universe displayed inward from the boundary, so that every telescope, every satellite, every instrument humanity builds shows us exactly what the builders want us to see. Scientifically, the hypothesis has a fundamental flaw that prevents it from being taken seriously in a formal sense. It is unfalsifiable. There is no observation you could make, no experiment you could design, no data you could collect that would prove you are inside a planetarium, because any evidence of the simulation could itself be part of the simulation. But it is also logically consistent with everything we observe. Nothing in the laws of physics prevents a sufficiently advanced civilization from building such a projection. Whether the planetarium hypothesis describes reality or not is beside the point. What it exposes is something uncomfortable about this entire investigation. Every explanation for the silence, the great filter, the dark forest, the zoo, the temporal coincidence argument rests on the assumption that we are seeing the real universe as it actually exists. If that assumption is false, every conclusion built on top of it collapses. The hypotheses pile up. Filters that kill civilizations before they expand, forests where civilizations hide from each other, zoos where advanced species observe primitives, planetariums where observed reality is manufactured. Each answer raises new questions, and none of them is testable with current instruments. But there is one hard fact that cuts through all the speculation, because it is neither a hypothesis nor a thought experiment. It is a measurement taken from the geological record of our own planet, and it makes everything hard to explain. Life appeared on this planet almost immediately, and then it stayed single-celled for 3 billion years. 3 billion years where nothing visible happened on the surface. Microbes floating in oceans, bacterial mats coating rocks, chemical exchanges in deep-sea hydrothermal vents. No plants, no animals, no eyes to look at the sky. Just chemistry complexifying with agonizing slowness. Then, roughly 600 million years ago, something changed. The Cambrian explosion. In the span of 20 to 25 million years, a blink in geological terms, nearly every major animal group we know today appeared in the fossil record. Eyes, legs, shells, claws, nervous systems, as if someone flipped a switch. 3 billion years of microbial silence, then an explosion of complexity that filled every available ecological niche in a geological instant. Nobody knows for certain what triggered the Cambrian explosion. Hypotheses include a rise in atmospheric oxygen levels, the thawing after a snowball Earth era where the entire planet was glaciated, or evolutionary innovations like predation that triggered a biological arms race. Whatever the cause, the transition from simple to complex life appears to require an extraordinarily specific set of conditions that took 3 billion years to assemble on Earth. That 3 billion year gap may be the filter itself, not the origin of life, not the emergence of intelligence, but the jump between the bacterium and the first multicellular organism. If that jump requires conditions as particular as Earth's, as dependent on a precise sequence of geological, atmospheric, and chemical events, then 40 billion habitable planets shrinks to a much more modest number. Most may be populated by eternal bacteria, living but silent worlds. Oceans teeming with microbes that will never evolve into anything more complex because the conditions will never be right. There's an austere beauty in this idea. The galaxy would be full of life, flooded with biology, but all of it microscopic and invisible. Billions of planets carrying life forms that will never build a radio, never smelt metal, never look at the stars wondering if someone else is there. Life would be common, intelligence would be the exception, and technology would be an anomaly so brief it would vanish before it could be seen. Fermi's question still echoes in the Los Alamos cafeteria. 75 years have passed, and we still don't have an answer. We have hypotheses, we have data. We have instruments of a power Fermi couldn't have imagined, and we have a number, the same number as in 1950. 0. That 0 doesn't say the universe is empty. It says something in the process that leads from a rocky planet in a habitable zone to a radio signal crossing the stars is either incredibly difficult, incredibly brief, or both. And we, sitting here in the 127th year of our transmission window, not knowing how long that window will stay open, have the strange, dizzying privilege of being the only known example of a species that asks the question. In a universe of 40 billion potential homes and 0 confirmed neighbors, we are the single voice that breaks the silence. And whether that silence is proof of our cosmic loneliness or simply the result of a window too narrow and distances too vast, the fact that we are here to hear it may be the most extraordinary thing this universe has ever produced. The antennas are still turning, the silence endures, and somewhere on one of those 40 billion planets, chemistry may be crossing the border into life right now. Maybe in 3 billion years, something on that world will look up at the sky and ask the same question. Maybe it will hear the same silence. Or maybe, if we last long enough, if we keep our telescopes running and our civilizations standing, maybe it will hear us. The faintest of whispers crossing the void between the stars. A signal saying simply, "We were here, we searched, we listened, and we held the window open as long as we could." But there's one aspect of this investigation that deserves examination from an entirely different angle, because it doesn't concern what's happening in space. It concerns what's happening here on Earth, in the way we search, in the choices we make about which instruments we build, and which ones we let die. The story of destroyed telescopes isn't a series of unfortunate coincidences. It's a revealing pattern of how humanity treats the one question that could fundamentally redefine our place in the universe. Big Ear was demolished to make way for a golf course. That wasn't vandalism, it was prioritization. The land was worth more as a leisure course than as an ear aimed at the cosmos. When Arecibo fell and the National Science Foundation chose not to rebuild, it wasn't a lack of technology, it was a lack of budgetary will. When the US Congress killed NASA's SETI program in 1993 for $12 million, a senator from Nevada decided that searching for cosmic neighbors was a waste of taxpayer money. $12 million. The Pentagon spends that before lunch on an ordinary Tuesday. There's something deeply ironic about a species that wonders why it's alone in the universe while systematically destroying the instruments designed to find the answer, so it can build golf courses and housing developments. If an extraterrestrial observer were monitoring our planet, it would see a civilization asking the most profound question imaginable, and then dismantling the tools to answer it. It would be forgivable to conclude that this species doesn't actually want to know the answer. And maybe it doesn't. Maybe the answer is frightening because both options are terrifying. If we are alone, the cosmos in its unfathomable immensity has produced only once what we are: intelligence, consciousness, the capacity to look at the stars and understand what they are. All of it would be a one-time accident in a 13.8 billion-year-old universe, a snowflake in a desert, and the responsibility of preserving that accident would rest entirely on our shoulders because there would be no one else to pick up the slack if we fail. If we are not alone, the implications are even more dizzying. Something in the galaxy is common enough to produce life, but hostile or indifferent enough to prevent any civilization from leaving a lasting trace. Garrett's and Dugan's filters aren't theoretical abstractions. The first describes a technology we are building right now, artificial intelligence advancing at a speed that alarms even its creators. The second describes a demographic trend visible in the census data of every developed nation on Earth. These aren't hypothetical future threats. They are processes already underway. Look around. Global birth rates are falling. Generative AI made a qualitative leap in 2022 that domain experts didn't expect until 2030 at the earliest. We are 127 years into our first radio transmission. If Garrett is right, we have 73 years left. 3 human generations, the time it takes a child born today to become a grandparent. That may be all that's left of the window. Not because a sudden catastrophe will strike, but because the relentless logic of technological improvement will transform our civilization into something we wouldn't recognize, and that might no longer be interested in sending signals into the sky. Fermi's question doesn't only ask where the others are, it asks, implicitly, who we are. Are we a civilization that will search for the answer to the end, that will keep its instruments running, that will resist the filters threatening us? Or are we one more civilization on the long list of those that flickered and vanished, adding our own silence to the accumulated silence of billions of years? The antennas turn, the silence waits. The window is still open. For how long? Nobody knows. But as long as it is, as long as a single human being somewhere on this planet looks up at the night sky and wonders if someone else is doing the same thing at the same moment, the question stays alive. And a living question is already an answer, maybe the only one we'll ever need. And in that silence, there may be the most important lesson this investigation can offer. We search for signals in the sky while forgetting that we are ourselves a signal. Every radio telescope we build, every probe we launch, every question we ask, the cosmos is proof that something extraordinary happened on this rock, 7,918 miles in diameter, orbiting an ordinary star in an unremarkable spiral arm of one galaxy among 2 trillion others. We are the proof that chemistry can become biology, that biology can become consciousness, and that consciousness can look at the stars and wonder why they are so silent. Fermi's question is not just a question about astronomy. It's a question about the fragility of everything we are. Every civilization that may have existed before us in this galaxy probably looked at its own sky with the same wonder, the same curiosity, the same cosmic loneliness. They may have built their own telescopes, listened on the same frequencies, waited for the same signals that never came. And then, one by one, they went dark, consumed by their own creations, dissolved by their own demographics, or simply gone so quiet that the difference between existing and not existing became undetectable. We have the unique privilege of knowing this story, of knowing the window is narrow, of understanding the mechanisms that threaten to close it. AI is advancing, birth rates are falling, telescopes are crumbling. Each of these is a clock ticking, and we don't know how much time remains before one of them reaches zero. But we know one thing the data can't measure and the equations can't capture. We know we're still here. The antennas are still turning. The data is still accumulating. The questions are still being asked. And as long as they are, as long as a conscious being somewhere in this vast and silent universe refuses to accept the silence as the final answer, the window stays open. Just a little longer, just a little wider, just enough that maybe, someday, something other than silence answers back.